physics is pretty much all about solving differential equations. I mean, some of those are, fairly easy differential equations, and some of them not so easy. And even at the beginning, you may not even know that you're solving it, but it mostly is. Mostly. Okay. So what I want to do is to go through three methods to solve the same differential equation. And I picked one that's kind of easy just to show you how it works. And let me go over these three methods. This is a differential equation with boundary conditions. So boundary condition says I know the value of the function at two different points. Now, the most common thing that you'll see in introductory physics is a differential equation with initial conditions. So this is an equation that depends on time, and you know that the position at t equals 0 and the velocity at t equals 0 or something like that, and that's a little bit different. So this is a boundary condition differential equation. So the three methods I'm going to show you are, number one, an analytical solution. This is what you would do if you can. I'm going to solve this one. That's why I picked an easy function so I can actually do it. The next, I'm going to do the shooting method. This is a lot like the way you would solve time-based differential equations, and maybe you've already done one of those and you didn't even know it. And then the last is the finite difference method, and this is one that works better for boundary conditions than that one, but they can both work. Let's get to it. So here's my differential equations. It says that if you take the second derivative of some function f with respect to x, it's going to be equal to x squared minus 2. And I have the boundary conditions of that function at x equals 0 has to be 0, and f at 3 has to be equal to 2. So let's solve this analytically. And like I said, yeah, I picked one that's easy. A lot of times you would do these other methods because this would not be easy. But I want to show you the solution in all three ways, so that's why I'm doing it. Well, the first thing we can do is if we think about a derivative, and in calculus, one of the coolest things is that then integral is an antiderivative. So if I integrate both sides with respect to dx, I can undo one of the derivatives. So let's do that. So let's say, I'll do it right here, the integral of df dx squared dx is going to be the integral of x squared minus 2 dx. So this is just going to be the first derivative. And now I can integrate that because this is an easy function, easy thing that I picked. I can use the power rule, so I get x cubed over 3 minus 2x. Now I do have a constant, so I'm going to say plus c, because I didn't do a definite integral. There's some constant that would still be the solution there. And let's just leave that constant there for right now. Now I can do the same thing again. I can integrate with respect to dx. Integrate with respect to dx. And now I get f. F as a function of x is going to be x to the 4th over 12 minus x squared over 2, but the 2's cancel. And there's a constant right there. I have to integrate that too, plus cx. And now I'm going to have another constant, plus b. And there's my function. I don't know the value of c and b, but I can find it if I apply the initial conditions. So let's do that. F of 0 is going to be equal to 0 to the 4th over 12 minus 0 squared plus c times 0 plus b. And that's equal to 0. So the only way for this to work is if b equals 0. And now I can do the same thing with my other boundary condition. F of 3 equals 3 to the 4th over 12 minus 3 squared. Oh, I was thinking in my head. 3 squared is 9. Plus c times 3 equals 2. Now I just need to solve this for c. And I mean, I don't think it's really difficult, and I don't want to waste time. So I'm pretty sure c equals 11 minus 81 over 12, all of that over 3. So now I have my function. Now, because we're going to do this more than one way, I want to actually make a plot of this function. Not that function. This function. So let's plot this function from 0 to 2, just so we can compare it when we find our other methods. So I'm going to switch over here to Python. I'm going to make a graph in Python. So if you haven't done graphing in Python, I mean, that's cool. You can follow along. But I use GlowScript VPython because this has a lot of built-in functions into it, especially easy for graphing. I can share the code with you, and I'll give you the link down below. And finally, the other thing is that you don't have to install anything. It's just running in a web page. I think that's awesome. Okay, so let's just make a graph. I have some tutorials on graphing. Hopefully I'll remember to include them. G1 is graph. X title, I'm going to do this even though I don't have to. X title is X. Y title is F of X. And let's do this. Width equals 500. Height equals 250. Excuse me. Now I need to make a function. Let's call it F1 equals gcurve. Color equals color dot blue. And now in order to plot the function, I'm actually going to make a function to plot the function. I'm going to make a Python function because it is a function. Why not? And I'm going to call it FF just so I can reuse the word F later below. So let's say def FF with some value X. And yes, I'm going to use the X globally and in the function. And that's a bad idea. And I'm a bad person for doing that. But it just makes sense and it works. So the first thing I need to do is find that value C. So I'm going to say C equals, I'm looking at my equation right here, 11 minus 81 over 12, all of that divided by 3. Now I can just return the function that I know for X. I can say return, let's see, what was it? X to the fourth divided by 12 minus X squared plus C, X, CX. No, XX, C times X. Okay, so now let's just check. Print FF of 0 should be 0. Print FF of, what was it, 3. It should be 2. Let's run that and see if it works. And it didn't. Because I misspelled return. Look at that. Return, ha. And it still didn't work. Assign to R value 20 def X FF. I wonder if it has something to do with this. Let's get rid of these. No. C equals 11 minus, oh, do I know? That's fine. Divided by 3. Return X squared. Oh, that's why. Minus. There. 0. It worked. Okay. Now I can just go through and make some X values and plot them. I don't need these anymore. That was just a check. So I can say X equals 0, dx equals 0.01, while X is less than, I'm going to 3. And now I just need to plot it. So I can say F1.plot X, FF of X. That's what I like about making that function. I can plot the function right there. I'll evaluate it and plot it, done, everything. Now, here's the thing I always forget. X equals X plus dx. If I don't do that, it's not going to increase. I'm going to get stuck in an infinite loop, and I'm going to cry. So I will not get stuck in an infinite loop, and there is your function. And that's my solution. I'm done. Okay, so I did that analytically. I plotted it just so I can compare it to later, and let's save this. Diff EQ analytical save. And I'm going to give you the code down below. Okay. Now, the shooting method. We're going to use the shooting method. Let me go back over to the paper and we'll do the shooting method for the same problem. Okay, so here is my, I'm going to copy down my equation. D, the second derivative of f with respect to x squared, x second derivative of x is x squared minus 2, and f of 0 equals 0, f of 3 equals 0. Okay. First thing, I'm going to really make a substitution here. I'm going to call this f double dot. So I'm going to say the second derivative of f with respect to x is going to be f double dot. So the double dot means the second derivative with respect to x. And then I could say this, df dx is f dot. And 1, I just think it looks cool, and 2, it's going to save us a lot of time too. So let's say that I'm going to use the Euler, this is the Euler method of solving a differential equation. So if I can write f double dot as this. delta f dot delta x. So the second derivative of f is equal to the change in the first derivative with respect to x, and this is not true because I have chosen a finite. This would give me actually the average f, right? So let's say if I break this into small pieces of x, then I can actually write this as f2 dot minus f1 dot over delta x. So imagine that here's my f1, 2, 3, and I have some functions. So I can say that's my f2, this is f dot, and this is x. So I can take this equation and solve for f2 dot. I can multiply both sides by delta x and add f1, and I get f2 dot equals f1 dot plus f double dot delta x. So this says that if I know the function, the derivative at point 1, and I know f double dot, I can find the next position. Now this is not true because as I move from 1 to 2, the value of f double dot is going to change. So I'm assuming f double dot's constant, and I can actually calculate f double dot as x squared minus 2. So I can do that. I can calculate the value of f double dot using x1 and plug it in right there and use that to find f2 if I know f1 dot. Right? I have to know the first f1 dot, which I actually don't really know, but that's fine. Okay, so then what I can do is to take the derivative of f dot, say f dot is equal to delta f over delta x. So that's going to be f2 minus f1 over delta x. And I can do the same thing to solve for f2. f2 equals f1 plus f dot delta x. I'm going to put a 2 right there. So since I just calculated f2 dot, I'm going to use f2 dot down here, and that's going to be how I can find that. So now this says if I know f1 at some time, some position, I can find the next one using the derivative, which I would find up here. Okay, so this is how we're going to do it. Number 1, calculate f double dot. Use that to find f2 dot and f1, using f1 dot and that to find f2. That's my problem, because I don't actually know f1 dot, but that's fine. If I did, I could find the new f2 dot, and I could use that to find this. Now, this is the normal Euler method. In the Euler method, if I knew f1 dot and f1, I could find all the future f's. Okay, and that'd be pretty cool, but I don't. So here's where we're going to do the shooting method. I'm going to say f1 dot equals 0. I don't know. Let's just pick it. Okay, so I'm going to, number 1, calculate f double dot. Number 2, use that to calculate the new f2 dot. Number 3, use that to calculate the new f. And let's see what happens. Okay, I'm going to use the same code I have over here. So I'm going to go back down here and I'm going to say x equals 0, dx equals, well, dx is the same. I'm going to make another graph. Let's call it f2. f2 equals g curve, color equals color dot red. And down here, I'm going to say again, while x is less than 3. So the first thing I want to do is to calculate f double dot. So I'm going to call that as a variable. I'm going to call this as ddf, for double dot f. And it's going to be x squared, was x squared minus 2. Right? I know my value of x is 0. So I can calculate f double dot. Now I already said f dot, which I'm going to call df, is equal to 0. I just picked it. I don't know, I just picked it. So now I can use that to find the new f dot. So df equals df plus ddf times dx. So here is something important about Python. In Python, this is not the algebraic equal sign. This is the make equal to sign. So this is my old value of df, and this is my new value of df. And I'm going to multiply ddf times that and just add that up to there. So that's that. Okay, so now I can use that df to find the new f. F equals f plus df times dx. And now I can move x. X equals x plus dx, and I should plot it. And maybe I should have plotted it before, but it doesn't really matter. f2.plot x f. So that, remember, I picked df is equal to 0. I had to start with some derivative. I don't know what it is, so I just picked it. Okay, so let's run this. Something happened. F plus. I'm making a lot of mistakes right now, aren't I? F plus. Oh, I never said what f was. I do know what f was. Okay. I do know f at x equals 0 is 0. I do know that. That was one of my conditions. But I didn't know the derivative. Okay. There. So I picked an initial derivative, which was wrong, obviously, and I just calculate everything else. Okay, well, let's just try. I want this. I know it's not right because this final value has to be the same as this final value. Well, maybe I picked wrong. Maybe df is 0.5. I'm going to pick 0.5. Okay, you'll notice it got a little bit closer. Let's pick 1. It's getting closer. Let's pick 1.3. Okay, let's pick 2. Okay, now you see what happened was my endpoint over there, my boundary condition actually went greater than that. So my initial slope's too big. I need to just make this a little bit smaller. Let's say 1.5. I think that's pretty close. Still too big, right? Because the function's too high. So I'm going to say 1.4. And here's the shooting part, right? I'm shooting to try to find the right answer. I'm shooting that what's my initial velocity, which I'm calling my df, until I get the right answer. So what was too big? Red needs to be 4 or 5. Let's try that. Pretty close. It's too big. Let's say 4, 4. And we could do this all day. But I think that's pretty good. They're right on top of each other, basically. And there's my solution. Now, this is a solution. But it's not the same solution, right? Really what I haven't solved for a function that solves it. I've solved for some data points that solve it. I have individual data points that look like a curve that I'm plotting. I have numerical values. If I don't have numbers, I can't do this. But this is the shooting method. And I think it makes sense to a lot of students to begin off with because you're using the Euler method, which they've probably used before. But in order to get that boundary condition, you have to adjust that initial value of the slope in order to get it to work. Okay. I should have saved this as something else, but I didn't. Now we have the finite, and there is a way that you could make that shooting method more automated. You could say, okay, keep increasing the slope until you get to the right value, but that's something for another day. I'd just rather show you what it is. You could use your programming skills, your programming ninja skills, or whatever you want to call them, to make that a much better program. But this is simple, right? And that's what I like about it. It's simple and easier to understand. So let's jump over to the finite difference method. Let me look at my notes real quick here, just to make sure I do it right. Okay. Jumping back to the paper. So here's what we have. F double dot equals x squared minus 2, f of 0 equals 0, f of 3 equals 2. And we want to solve that. So let's imagine that I have, let's say f dot as a function of x. And I have certain values for these. So there's finite values. So there's, let's call that 1, that's x1, x2, x3, not the values, x4. So there's that one, there's that one, there's that one. So they all have some f dot values. Well, I could also plot the same thing for f. And again, they're all, let's say they're evenly spaced, dx. A lot of times I use h. Actually, let's use h because that's what I have in my other notes. H separated by some value h. Okay, so what if I want to find f dot right here? I want to find the derivative at this point. Well, one way to do that would be to say, okay, I can use the definition of slope going from here to there, and it would just be f dot is going to be, that's going to be 0.2, that's 1. F dot 2 is f2 minus f1 over h. But that doesn't really take into account what's happening over here. So I could do it over here for these two, or I could go find the slope from here to there. So let's do that. If I find the slope from there to there, I can say f2 dot, because then it'll use the number before it and after it. It's going to be the one after it, which is f3, minus the one before it, f1, over this distance, which is going to be 2h. Okay, so that's what I can use for my derivative. I think it's a better derivative. Now, if I want to generalize that for any point I could say fi dot is going to be the number before it, so it's going to be I plus 1 minus fi minus 1 over 2h. So now I can put any i's in there, I can get the derivative. What about the second derivative? Well, the second derivative would be the same thing, except I could use, I'm using the change in slope. So if I'm plotting f dot, and I'm just trying to check my notes here, and in fact, I can use the slope here, actually the slope here, and the slope here, and assume we're kind of like in the middle of those as my slopes, and take the difference of those. So let's do this. Let's say f2 double dot is going to be the change in the derivatives. So that's going to be this slope, which is going to be equal to f3 minus f2 all over h, right? Because I'm just using one interval, minus this slope, which is going to be f2 minus f1 over h, and all of that divided by h. Is that what I want? Yep. Okay, so let's divide down by h, and I get h squared on the bottom, and so I can write this as f2 double dot equals f3 minus f2 minus f2 plus f1 over h squared. So I had the minus sign, minus f2, minus sign, another one right there, so I get plus. So this is going to be f3, then I get minus f plus f1 minus 2f2 over h squared. So that's my second derivative. If I generalize that, it looks like this. Fi double dot is going to be equal to fi plus 1, because we're doing it at number 2. So this is I plus 1. That's the one before it. F plus fi minus 1. And then minus 2fi, all of that over h squared. So that's how I can, this is a finite difference to find the derivatives. Now I can use this and set that equal to my function. So now I can say f double dot I is going to be fi plus 1 plus fi minus 1 minus 2fi over h squared equals xi squared, what is it, minus 2? Minus 2. So I can use this and solve for fi. So let's solve this for fi. So I'm going to multiply both sides by h squared. I get fi plus 1 plus fi minus 1 minus 2fi equals xi squared minus 2 h squared. And then I can just add this to both sides, divide by 2. I get fi equals, I'll do it in one, I won't do it all in one step. I'll just add that to both sides, subtract that. Fi plus 1 plus fi minus 1 minus h squared xi squared minus 2, and that can divide by 2. Fi is 1/2. So 1. Fi plus 1 plus fi minus 1 minus h squared xi squared minus 2. That's it. So this says that if I know the value of fi before and after this point and the x value, then I can find that point. And that doesn't seem useful, but it is. Because here's what we're going to do. This is what's called successive over-relaxation. Suppose I have some values for, this is f and this is x. So I have some values. And it doesn't really matter what they are. And this is x equals 3, or where am I at 3 at the end. I know that one is up here at 2. I know this is set. I'm going to put a box around it. I know that one's set, which is the first and the last piece. Those are my boundary conditions. They're set. I can just guess some data values over here. And with that, once I guess those values, I can then find the new value right here using these two values that I guessed. I can use the one before it and the one after it and plug it into this equation and find that new one. And then I can go over here. I can find my new value using these two, which I just guessed. And then I do the same thing. I can go all the way down up to here, the last one, where I guess I use my function, the endpoint in that one. And then they all have new values. And then I can do the whole thing again with my new values. So I just keep going over and over and over the data forever until I get these things not changing, and they'll satisfy that equation. I know that seems crazy, but it does indeed work. So the first thing I need to do is to start off with a guess of a function. And then I'm trying to think what I should use for the guess. Let's see. I'm using what I did before. My guess was x, no. I just had they were all just zeros. Okay, so let's do that. So let's go back to Python and make a new one more graph here. So I'm gonna make this f3 equals g curve, color equals color.green, and then I'm gonna do I think let's leave that off, that's fine. Okay, so the first thing I want to do is to pick a value for h. And what did I use before? 0.2. So I can say h equals 0.2. And I want to go through and I want to put all my values of x. I need to make a guess function. So when I'm dealing with all these values, I need to deal with them as a list. In Python, we're going to use lists. So I'm going to say this. xp is equal to an empty list. fp is equal to an empty list. fp2 is equal to an empty list. So I need two lists for the function f, because one, I'm going to have a guess value. I'm going to go through and put a value in there. I'm going to go through that and calculate new values, and that's going to be my fp2. And then I'm going to set my old values equal to my new values, and I can do it again. So I need two, kind of like leapfrogging. So let's go through and make our empty stuff that we can guess with. So I'm going to say while x is equal to less than x3. Let's see, what am I going to do? I'm going to put this as less than or equal to, because I don't have big steps. If you have small steps, you can make some dumb things and everything will work out okay, but I have larger steps. So the first thing I'm going to say is x equals x plus h. I'm going to actually move it forward one. Before that, I'm actually going to set my initial values up here. So I'm going to say xp. Let's see, what did I do? xp equals, yeah, xp equals xp plus x. So what this does is it adds one element to my list, and the value is x. Now I started off with x equals 0. Actually, no, now I did. So it's going to add a 0 in there. That's my first data point. Now I need to add in my first fp point. So fp is going to be equal to fp plus 0. And I'm putting 0 because remember that f of 0 is 0. That's my first data point. I'm also going to do the same thing for fp2, which is my new function, which I can just add that in there. Okay, so now when I go through the x values right here, I'm going to move x forward, and then I'm going to add to my new list. So I'm going to say xp equals xp plus x, right, new value. My fp, I'm just going to put them all at 0. fp equals fp plus 0. fp2 equals fp2 plus 0. Now once I get through the whole thing, I need to change the endpoints, right? Because I know that last value has to be equal to, what was it? 2. So I can access the last element in a list as fp negative 1. That's the last. fp0 is the first. fp negative 1 is the last. So this is going to be equal to 2. And I'm going to do that for also for fp2 negative 1 equals 2. Okay, let's go ahead and plot this. I want to make an animated plot because it makes me happy. So to do an animated plot, I actually need a data value to plot. So I'm going to say this: f data is going to be equal to an empty list. And now I'm going to go through all of my list of FPs and add to this data list. So for I in range I, I'll include a link down below for list stuff. Length of FP. So I is going to be each element, a number for each element in my list. I'm going to say f data equals f data plus this xpi, xpi, fpi. This is going to be an ordered pair, and I is a number. Now once I do that, I can actually plot it. So I can say f3.data equals f data, and that'll plot it. So let's just plot my initial function. I haven't done the finite difference yet. There it goes. So you'll see here I start off with f is 0. There's finite values up here. And there's my last one. They're big step sizes. How do you turn on the markers equals true? So if I go up here, markers equals true. Now I'll put little dots there. I like that better. Okay, so that's good. That's my first guess. Now I want to go through and change all those. Here we go. So the first thing I'm going to do is to do this. N equals 0, N equals 10. So N, capital N is the number of times I'm going to go through this list and change it. And N, lowercase n is my counter. So that way I can just keep track. And there's more than one way to do this, but this is the way I do it, and I'm fine with that. So the first thing I'm going to do is to say while n is less than n. And I'm going to say rate 50. Because I'm going to animate this, so I'm going to, this says don't do more than 50 calculations per second. So this only take a short amount of time, but that's fine. The first thing I'm going to do is clear my data to plot, right? Because I don't want to replot, I want to move everything. So I'm going to clear all that data before, and then add it in there again. Now for the magic. For I in range 1, length fp minus 1. And I'm going to print this. I'm going to print I. No, I'm not going to do that. I should have done that, but that's fine. So this goes from 1. It doesn't start at 0. It starts at 1, and it goes up to the 1 to the very last element, the second to last element of fp. So I'm not going to go through the whole list. I'm going to leave the endpoints alone because I can't calculate the derivatives for the endpoints because I don't have the ones before it. So I'm not going to do those. They're fixed anyway. They're boundary conditions. So now all I'm going to do is this. fp2 of I equals 0.5. I'm typing in that equation that I wrote over here. So it's half, and then I have fi plus 1. So I'm just going to say times fp I plus 1 plus fp I minus 1 minus h squared times xpi squared minus 2. I just typed in my equation just as I see it. Instead of subscript I put the square bracket I. That refers to that number in the element. Okay, so that what I went through the whole thing. That for loop right there goes through the whole thing and updates every element. But I need to now take the old elements and make it equal to the new elements. Here's a problem that I always made a mistake with. I'm going to do that with for I in range length of FP. FPI equals FP2I. So you can't put just FP equals FP2 because then it will I have pointers to the same data range, and if you change one, the other one changes automatically. It's going to be a disaster. Now I want to plot this stuff, so I'm going to say for I in range, and you could do this in the same step. Length FP, F data equals F data plus XPI, FPI. And then I'm going to say F3.data equals F-data. That will make the graph. And now I need to increase n. N equals n plus 1. Okay, let's see if that works. Okay, so you see, I went through 50 times. And every time it got closer to the real function. I mean, it's amazing that this actually works. So let's run it for longer. Let's do, that was 10 times. Let's do 50. It's not there, but it's close. Let's do it for 100. And let's make it go faster. I mean, it's not quite there yet. It's getting close. So let's just do 200. And let's make this run even faster because we're that impatient. And there you go. So now I actually have 3 functions there. I have an analytical solution, I have a numerical solution from the shooting method, and then I have a numerical solution from the finite difference method. And they all agree. And I think agreement is great. Couldn't we all just get along? But there you go. So, like I said, this is just an introduction to that. I'm saving the code right now. And all of that code is going to be linked down below. You really got to play with these things to really figure it out. I've made a lot of mistakes too, but there you go. I don't have anything else to say. This was a long video, longer than I normally do. Okay, solving differential equations. Hope that helps.